S. Chand presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
The most confusing part of the engineering mechanics course is the simple harmonic motion, and in this video we will be explaining that particular concept.
If you want to study this topic in detail, refer to the book by S. Chand Publishing. Link is provided in the description box.
Welcome to S. Chand Academy, and I am Anmol Bhatia. In today's part of the video, we will be learning about the harmonic oscillator, the simple harmonic motion and the damped vibrations. The topics that we would be covering are harmonic oscillator, the damped harmonic motion, and in that we have certain cases which is over damped, critically damped, lightly damped oscillators. So what is the harmonic oscillator? As far as the definition of the harmonic oscillator is concerned, in the harmonic motion what we can say that there is a point about which the system oscillates. Let's say we have a spring mass system, mass placed at a particular distance from the spring, and we keep on providing the particular amplitude. So this mass system with respect to the spring keeps on forming certain forces, keeps on oscillating. Now here if I place, let's say, a paper that keeps on moving from the surface, and I place a pencil here, so what will happen? It would create oscillations like this. So when this is moving and I have placed a pencil here, so I will get these oscillations. So here in the similar grounds there is a point about which the system oscillates. So there is a point about which the system oscillates, and there is a force which brings the mass again and again to the point where the force is 0. So it has a particular force that keeps on restoring the system at the equilibrium position. That force is called as a restoring force, and the point is called as the equilibrium point or the mean position. So here let's say we have an object, and that object, this object, we have tied a string to this object and we keep on rotating. This object keeps on rotating, and when this object keeps on rotating, so it has a periodic motion of the rotation, and this periodic motion has a time period associated, wherein the frequency of this motion is 2 pi divided by t. This is the expression associated. Then mathematically, if we want to look at this system in terms of engineering perspective, these two I have already explained about a restoring force and what is mean position or the equilibrium position. This harmonic motion can be expressed mathematically in terms of this Maclaurin's series. Here the force would be equal to force at x equal to 0, that means at that equilibrium position, plus x multiplied by the derivative of the same considering x as 0, then plus x square by 2, the double derivative considering x as 0, plus so on. So we have this expression which is Maclaurin's expression. So for the convenience we choose x as 0 as this equilibrium position. So herein we have this spring mass system, we have this mass and we have the spring attached to the mass on a smooth surface, and when we stretch or when we place this mass at a particular distance, that means we have this value of x, which is the amplitude. So what happens here, it results into the first term only, which is f at x equal to 0, which is 0. That means this term f at x equal to 0 comes out to be 0, and this amplitude no doubt is very small enough. So we need to have this, we need to neglect these x square quantities or x cube quantities or x power 4 quantities as 0, as a very small quantity, so that very small quantity can be neglected. So we have neglected all these quantities, and what we are left exactly is this part, fx equal to x derivative with respect to x at x equal to 0. Now the motion which is the resulting motion, that resulting motion is called as a simple harmonic motion, and the system which oscillates is called as a simple harmonic oscillator. So there is no point of confusion here. The only thing is the force associated. So force associated is this Maclaurin series x into the derivative of this force at x equal to 0. Now when I put this part, or when I replace this part with the constant, I will get this quantity which is k, and that particular expression is called as the Hooke's law. So fx equals to minus k times x, which is the Hooke's law. So what I can do, I can substitute this force as minus kx. That means force I know, which is m mass into the acceleration, and acceleration is a double derivative of this position, which is d2x by dt square, and that would be minus kx. So if I take this minus kx towards the left, I will get this expression which is m d2x by dt square plus kx equal to 0. Here the position vector or the position of this particular point or the particle is a cos omega t plus phi, where omega is 2 pi by t and fx is termed as the conservative force. Now we know that force is minus dv by dx, and if we want to find out dv from this expression, I will get minus f dot dx, and when I integrate it with respect to from 0 to x, I will get this particular expression. So I have told you that fx equal to minus kx, so minus into minus is positive, so plus kx into dx 0 to x. So when I integrate it and when I solve, I will get the value which is half k x square. That means I will have this value of energy associated with the particle as half k x square. So the harmonic oscillator would have this potential energy associated, and fx, I have told you that this is the conservative force, and so on. We calculated this expression which is half k x square, wherein half k x square is termed as the potential energy associated with this harmonic oscillator. Now graphically, if I want to look at the system, I have to check whether this system is a parabolic system or what kind of system. So considering the same system of the spring mass situation, I have a spring having the damping coefficient as k and the mass associated is m, and when I stretch this system, or when I stretch this mass to a particular distance, let us say x, which is equal to the amplitude x equals to a, in that particular situation I will get this value of energy as half k a square, substituting x as a. So this would become half k a square. At this mean at this mid position, x is 0, that means potential energy is 0, and when I substitute x as minus a, because this is towards the left, so at that particular time also this energy would be half k a square. So when I look at the situation graphically, I will get this graph which indicates the parabolic function, and these are the two different extremes. At one extreme x equal to a, and at another extreme x equal to minus a, and for that particular extremes we have the value of potential energy as half k a square. Now beyond this region we will not get the particle. So this region would specifically be called as a classically forbidden region, and this I will elaborate in the forthcoming slides, but as of now this region is called as the classically forbidden region. Now what conclusions can we draw from this simple harmonic oscillator type of system? So first conclusion that we draw from this simple harmonic oscillator system is that the allowed energy of the simple harmonic oscillator forms a continuous spectrum Now what is this continuous spectrum means? Let's say I have a rope and I want to pull this rope to a particular distance, let's say 1 meter, or let's say half a meter, 0.5 meter. So this is up to me that how much I can pull this rope. But let's say I have a system in which I have a ladder and the gap between the ladders is, let's say, 1 meter. So I want to step into the top of this ladder. So considering the distances of only 1 meter, I need to step in. That means I have a fixed set of values that I need to cover. I don't have any freedom to get that particular distance. So here in this system I have a freedom. I have a freedom of choosing the distances, let's say 1 meter or 0.5 meter or 1.5 meter. That particular system is called as a continuous spectrum. Here also we have a freedom of choosing the energy associated with the system. Let's say if I want to make the system of, let's say, 2 joules, I can make it. I want to make a simple oscillator of energy 1 joule, I can make it. So how much minimum I can make? The minimum energy oscillator that I can make or that is possible is 0. That means we can make the simple harmonic oscillator of 0 joules. So beyond the 0 joules it is not possible. Then the next thing is the particle can oscillate only within the statistical limits, which is plus minus a, that I have explained the same in this graph, that the particle can oscillate from this region to this region, and these two regions are the forbidden zones. So plus minus a is that limit in which the particles can particularly oscillate. Then what do we have? The probability of finding the mass of the system, wherein if we want to capture or we want to check that at what particular location we need to have the system. So let's say the pendulum is oscillating at a particular frequency. So we want to find out or we want to analyze wherein those particles are. So the particle at this central location would be having some velocity, but when the particle reaches to the topmost point or reaches to the extreme position, it would stop for a particular location, and then you will get those particles there. But in the mean position they are continuously moving. So at that particular location you will not find those particles. So here the point of conclusion is the probability of finding the mass is at that location wherein we can find that particle. So the probability is maximum at the extreme position, and then the probability is minimum at the mean position, because at those extreme positions the particle would stop certainly for a period of time, and at those mean positions the probability is minimum. And we have a probability 0 at those forbidden regions. That means when x is more than a and when x is less than minus a, that means the region of forbidden zones. That means at this particular regions will not find those particles, rather the particle will come to this position and then it will turn back. So this is the third conclusion that has been drawn, the fourth conclusion that has been drawn from the system. And the fifth conclusion is any sort of potential energy curve can be approximated as a parabolic function near its local minima. So I have told you that the spring mass system is continuously moving from top to the bottom position, and if we place a pencil over the surface and continuously spreading the sheet, continuously stretching the sheet from the system, we will get a curve like this. And what do I want to find out? I want to find out the potential energy, and that potential energy can be approximated as a local minima of the system. So what is this local minima of the system? If we approximate a curve and after approximation if I get this point, and that point is called as a point of local minima, this point is termed as a local minima point. This local minima point is the point of getting this potential energy from the system. We stop here for a short break After coming back from the break, we will learn more details of the harmonic motion.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back after the break. Before going to the break, we have learned the details of harmonic oscillator. Now we will be discussing about the damped oscillations. So damped oscillations, or specifically they are called as damped harmonic oscillations. What is it? So if a body is moving in a simple harmonic motion and a simultaneous resistive force is acting on it, so the amplitude of these vibrations gradually decreases, and at one particular time they will come to the rest position. That particular oscillations are called as damped harmonic oscillations. Now what does it mean? Let's say we have a simple harmonic oscillator that produces the oscillations like this, and we have a category of the resistive force that is acting on the oscillator. So when this resistive forces are acting, so you can observe that the amplitude of these vibrations are decreasing continuously. So the amplitude is decreasing, and at a final position it will come to the rest. So those are called as the damped vibrations, so or the damped harmonic oscillations. So coming back to the definition again, so as I have told you that this body is moving in a simple harmonic motion, and there is a resistive force which is acting on that body, and the amplitude of that particular oscillations, they are gradually decreasing, and at what particular time it would come to the rest, and when it comes to the rest after a specific period of time, that is called as a damped harmonic oscillation. So this is the situation of the damped harmonic oscillation. Now coming to the engineering aspect of the damped harmonic oscillation, we need to understand this mathematically. So as I have told you that there is some force which is the resistive force which is acting on the surface. So that resistive force is directly proportional to the velocity, and when this directly proportional sign is removed, so equals to gamma times the velocity would come into the picture. Now what is this gamma? Gamma is force per unit velocity. So as you can see, when I substitute force per velocity, so velocity and velocity terms gets cancelled out, so I will only get the force associated. Now if I want to replace this velocity by a derivative, so I need to write it as dx by dt. So this resistive force would be equal to gamma dx by dt. So we will keep this gamma dx by dt safe side in this equation number 1. Then whenever this damping or whenever this harmonic oscillator produces some oscillations, then there is a restoring force which is there into the picture. So there are as of now two forces which are there into the picture. One is the damping force, which is responsible for bringing this oscillations to the rest position, and the next thing is the restoring force, which is minus Cx, or you can say the minus Kx part. Now as per the Newton's second law is concerned, force is equal to the sum of all these two components of the forces. So first component is this minus Cx, and the second component is minus gamma dx over dt. Force, as you know, is mass into acceleration, so I have replaced this acceleration term by this double derivative, which is d2x by dt square, that is equal to minus Cx minus gamma dx by dt, and this mass is multiplied by this entire equation. So I will divide this mass and take this mass value towards the right hand side. So what do I get? Minus c by mx minus gamma by m dx by dt. So this c by m is denoted by the term which is omega square, and gamma by m is denoted by the term 2k. So where k is specifically called as a damping coefficient of the spring which is associated to the spring mass system. So when I club this equation, I will get this final equation of this damped oscillations, and this final equation would be d2x by dt square plus gamma square x plus 2k dx by dt. This is the equation of the damped oscillations. Now what I want to do, I want to get a solution of this differential equation. So in order to get the solution of this differential equation, I will have this factor, or I have this solution of this damped oscillation equation, which is x equal to a into e raised to the power alpha t, where a and alpha are the constants. So I need to derivate it because I want to put this in the expression. So after differentiating with respect to t, what do I get? A is constant, so a remains constant. E raised to the power alpha t derivative is e raised to the power alpha t into alpha t's derivative, which is alpha. I need to substitute d2x by dt square also in the equation, so I need to derivate this also, which is a e raised to the power alpha t derivative is e raised to the power alpha t into again 1 alpha. So a alpha square e raised to the power alpha t. Now I have this value of dx by dt and I have this value of d2x by dt square. I need to substitute the same in this expression, d2x by dt square and dx by dt. So after substituting the same parts in this expression, I'll get this final expression. Again solving this final expression for the solution, what do I get? I need to solve this by the quadratic formula. This constant would be 1, this constant is 2k, and this constant is gamma square. So a is 1, b is 2k, and c is gamma square. Considering the solution, which is minus b plus minus root b square minus 4ac over 2a, so I have to find out the solution, which is minus k plus minus under root k square minus omega square, and that equation would have this general solution, which is two constants, a1 e raised to the power alpha 1 t plus a2 e raised to the power alpha 2 t. And what is this alpha 1 and alpha 2? Alpha 1 is the equation with the plus sign, and alpha 2 is the equation with the minus sign. So here we have alpha 1 and alpha 2 as the solution. So as far as the general solution of the differential equation is concerned, I need to substitute alpha 1 and alpha 2 in this equation, so as to get the overall final equation, where you can see a1 and a2 are the two constants, and alpha 1 and alpha 2 were the solutions that I have got from the equation. Now I have this k part and I have this omega part. So the formula, as I have already mentioned, k is gamma over 2m and omega is under root c by m, wherein this term k square minus omega square within the root is very important, and that particularly depicts the engineering aspect of the same. Now what is this engineering aspect associated? Now let us say if we want to have the particular vibrations of the oscillator, so if we want to create those particular vibrations from the oscillator, we need to look at this term. Let us say if we want to have the oscillations of the type heavily damped, so I need to have this expression as positive. That means k square is greater than omega square. And when k square is equal to omega square, I name that particular type of equation or the particular type of system as critically damped. And when this k square is less than omega square, that means this thing is particularly negative, then the type of oscillations that are to be produced is lightly damped oscillations. So this is the case. So far we have learned about the damped harmonic oscillations, in which I have told you the definition of the damped harmonic oscillations, and we have derived one solution out of the expression that we derived for the damped harmonic oscillations, and we have initiated 3 different cases which are heavily damped, critically damped and lightly damped. So, with this we come to the end of the video which was based on the damped harmonic oscillations. From there we derived 3 different cases. One is the lightly damped, critically damped and the heavily damped. Now, in the next part of the videos we would be learning about the derivations which is based on the engineering aspect of these 3 different cases.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.